We now begin part 6, right, of this AC. And 6.1, we're going to talk about the use of transformers. This is what a transformer looks like, right? We hardly see this in Singapore. And if you travel north in Malaysia, there are some chance that you can see this. And in some of the photos that I've seen of the streets in Philippines, in the more rural areas, and in Brazil, I do see this around, right? Right, so like I've said, why should we use AC? Well, because voltage can be easily stepped up or down using transformers, and because you have high voltage, we can decrease the current, and by decreasing the current, the energy loss in the cables will be much lower. Okay, and if we want to overcome the problem of having high voltage, we actually can step it down again easily, right, to a more safer and practical voltage of 240 volts. Okay, let's take a look at the diagram, circuit diagram, and the picture here. Right, so if your power plant is the source here, you have a transmission substation here, right, which will step up the power. I combined all the power lines before your home into these two parts. Of course, there are a few more, but I skipped the details. And then at the transformer drum near your home, it steps down to 240 volts for you to use at your home. Okay. Let's now talk about a little bit more about a transformer. A transformer is very useful to step up or step down the AC current. So essentially, a transformer consists of two coils or wires that are electrically insulated from each other but wound on the soft iron core. Okay, so the power that is passed to the primary coil is then delivered to the second coil. Okay, this is the symbol for a transformer. Do you own a transformer? Right? If you look at your laptop or your phone charger, right? Your laptop charger or your phone charger, that essentially consists of a transformer, right? Because it's required to convert it from 200 volts AC to a lower required voltage, right? So there is a transformer inside. And second, there will also be a full wave rectification circuit with smoothing to change it into a DC. Okay. Right. So now let's look at example number 7 to have an idea why AC can help you save money, right? So you have a nuclear power station that can generate 2 megawatts of electricity, and the electricity is sent through power cables, right, which has a resistance of 5 ohms. In Singapore, our power cables that's used to transmit electricity are all buried underground. If you drive up north, right, to Malaysia, you can see pylons, right, along the north-south highway, and those are actually the cables that we are talking about. Okay. So part A, what's the power loss in the cables? So we first step it up to 500 kilovolts. So if you remember the equation, power equals V over I. If your power is 2 megawatts and the voltage is 500 kilovolts, the current through these cables, right, will be 4 ampere. Next, if you want to find then the power loss in the cable, it will be the current through the cables multiplied by R. So you get 4.0 times 4.0 square times 5, you get 80 watts. What is the voltage drop across the cables? Right? You can use V equals IR and can get 4 times 5 equals to 20 volts. Therefore, the output voltage at the destination load is this value, 500,000 minus 20. Okay. So here I want to talk about a certain point, right? Of course, your home doesn't have 499 kilovolts across it, right? There's a step down here. But look at this equation, right? We calculated the power loss using I squared R. strongly recommend to you to use this equation to calculate the power loss. There are students who use P equals to V squared over R. Can, but you must know clearly which V to use. In the past, when the students use V squared over R, there are many students who use the V across the power station rather than the V drop across the cables. If you want to use V squared over R, you should use this V. 20 squared divided by 5 gives you back 80 watts, which is the power loss in the cables. If you use 500 kilovolts square divided by R, you will get an insane amount of power loss, right? Which is not correct. So this is something for you to take note, right? I strongly recommend using I squared R to find power loss in the cables rather than V squared over R. Okay. Next, part D, recalculate the power loss in the cables if the input voltage was 100 times smaller at 5 kilovolts instead. So we're repeating part A. If the input voltage is 5 kilovolts, using P equals to VI, the current is 400 ampere. Using I squared R, you lose 800 kilowatts. So for a power station of 5 megawatts, you are losing 800 kilovolts, which is 0.8 of a megawatt. That's essentially saying for every $5, you are roughly losing $1. I think that's not very smart, right? Whereas in the previous example, for a 5 megawatt power station, you're only losing 80 watts. So that is essentially losing a fraction of a cent for every dollar of power you have, right? So I hope this example proves to you why using AC is a much better method. With this, we have come to the end of part 6.1.